Hello class, welcome to Physics 340. Today I'm going to be teaching you the basics of how to draw free body diagrams, just in case you didn't learn how to do this properly in Physics 150. This is a skill that I admittedly did not learn when I took Physics 150. I was in upper level mechanics course similar to you. When a professor gave us a very simple problem to do, we all failed it, and he then gave us another problem set called problem set 0. You could turn it in as many times as you wanted. That was the inspiration for the problem set that you guys will be solving today. I'm going to show you how to solve a system like the following, which is hopefully simple to all of you, but just in case it isn't, let's go ahead and do it. So first thing you do is you draw a picture. Okay, free body, the free and free body diagram means free from the picture. You do not draw free body diagrams on your picture. Sometimes it's fast, sometimes it's convenient, but we do not draw it on our picture. So first thing you do is you have to figure out which object is the simplest. I'm going to contend that object 2 is the simplest because it is touching the least number of things. So we will draw a single dot representing object 2. There we go. Put a little 2 next to it to remind us that's what it is. Then once you've drawn your dot representing the center of mass of that object, you will draw all the forces acting on that object. When you do not have to calculate things like torques, you assume that all of your forces act through the center of mass. We'll get into more complicated circumstances later on, but right now I'm just going to start doing it. I really recommend that if possible you print out or even write out the steps to doing free body diagrams that I have posted on Moodle. Those are going to be invaluable to you on this problem set. Note that in this recording you might hear children in the background, as the rest of you are likely locked in your home, so am I, with 3 small children who may come in and you may hear me talking to them. As I get better at video editing, I will remove them from the videos as able, but for now you're probably going to hear some awkward audio, and well, that's just the way it is. Welcome to Physics Spring Quarter. Okay, back to the problem. We have a dot representing box number 2. We're going to draw a vector representing its weight. We always do non-contact forces first. Okay, and so it doesn't really matter how long you make that first vector. However, it will now be the vector for which you set the scale of all of your other vectors. I've chosen 2 boxes because it's simply convenient. Now, once you've done that, you then want to trace your object. What do I mean by that? Meaning you want to basically take your pencil and think about tracing the whole outline of that object. And only where you see contact will there be a force. I always recommend that you start tracing not at the bottom, but you pick one of the sides. So we will now do that. I will trace it. There's nothing on this side. No forces, nothing on this side, no forces, nothing on that side, no forces. Now here at the bottom, we have a contact. And whenever you have 2 surfaces contacting, you have the possibility of 2 forces, what's called a normal force and what's called a frictional force. Okay, just a side note, if you didn't know this, normal is code word for perpendicular. That means the force that is perpendicular to your surface. So let's go back to our free body diagram. What do we get? We're going to get a normal force. Now, many people think, oh, the normal force is going to be pointing upward. That's true. The 2 surfaces are contacting one another. So I'm going to draw it upward. Now, in this case, it will turn out that the normal force, which we will label as N21, that stands for normal onto due to 1. This is the convention that I require that you use to this course, even if it's not the convention that you're used to. You have to learn to adapt, so I'm asking you to do that now. So that's the normal force onto due to object 1. Now, I've drawn it the same length as the weight vector because I know where this is going. However, in general, you do not know what the length of that normal force is going to be. You always have to solve for it. All right, then we can have a frictional force. Well, if we had a frictional force, the question is which way would it be? We're not given any information yet about this problem. We're not told it's speeding up, slowing down, at rest. So without any information, you assume that your system's at rest. If you look at your picture now, adding a frictional force left or adding a frictional force right would create a net total force when adding up all of those vectors. Since we assume the system's at rest, we may not have a net total force, and therefore we require no friction. We are now done with that free body diagram. We will now go on to the next free body diagram, which will, in this case, will be object number 1. So I'll put a single dot representing object number 1. First force you add is your non-contact forces. In this case, it will be gravity. I will assume that because block 1 is drawn larger than block 2, that it has a larger mass, therefore it has a larger weight. So now that I draw its weight vector, it will look something like the following. And I will label that m sub 1 times g. Okay. A note, whenever working with introductory physics students, they often think that this is m1 sub g, as if g is somehow a subscript. That's very strange. Hopefully none of you think that, but if you do, hopefully you don't now. All right, so we have that, and the next thing we do is we trace our object. There is no forces here. I get to this point, aha, there's contact. That contact results in the Newton third law pairs of those forces. So we now have a normal pointing downward. We'll draw it to length 2 to correspond with the length of that vector. Okay. And so now we have a normal force on 1 because of 2, and that one's pointing downward. We then allow there to be friction, which there is none because there was none in the prior diagram. We continue our trace. There are no objects, no touching until we get to the bottom. And then again, at the bottom, we're allowed to have a normal and friction. So in this case, we'll have a normal. How long is it going to be? Well, we need that normal force to cancel out the sum of those two vectors. So that normal force is going to be pointed upwards, and in this case, it's going to have a length of 6, which is larger than I've allowed for in my diagram here. So I'll reposition myself, and we'll go from there. So now we'll draw it up here. And so here we have a normal on object 1 due to, say, the surface, due to ground, whatever you want to call it. Okay. So now we see immediately that while these normal forces are third law pairs and equal to one another, we also see that this weight is going to equal that normal force, but not because it is the normal force. We see that this normal and that weight are the same, but this normal and that weight are not the same. So please get out of that really bad habit of assuming that normal equals weight. Okay. So the next thing you do is, once you've drawn your free body diagrams, you ask yourself, do I have any constraints on my acceleration? Well, in this case, nothing's accelerating, so there's not really a lot of constraints to talk about. If both the objects were moving together and didn't separate, you could say something like A1 would equal A2, but we're not told anything about that right now. So what we're going to now do is put a coordinate system on our system. Each of these blocks get their own coordinate system. I'm going to just make a pretty standard assumption, x and y. Now, why are we choosing that coordinate system? Well, we want to make sure that if we were to accelerate, in this case it would probably be horizontal, that our acceleration doesn't have to further be split into components. That is, whenever it's possible, you don't want to split acceleration vectors into components. It just makes the algebra harder to do. So now, step 1, you draw your picture. Step 2, you draw a free body diagram for each object. Then you go on and do your coordinate system, and then the last thing you do is you sum your forces. This is all very mechanical, very rote approach. We're not thinking about anything right now. We've drawn the pictures. All the hard part is over. So we will now sum our forces on object 2. We'll start in the y direction, and we see that the sum is n21 minus m2g equals m2a2, and this is in the y direction. However, again, we're assuming that this is at rest, so therefore we'll take that to be 0. We then therefore solve for n21 is equal to m2g. So now this is important. This is why we know that that normal force will equal those weights there. It's only at that step that you actually know how long those vectors are, which means sometimes at the end of the problem you have to erase your free body diagrams or you have to draw new ones. All right. So now we'll continue on. There's nothing in the x to worry about. Now we'll sum our forces on object 1 in the y direction, and we're going to get that n2 by the surface, 1 by the surface minus n12 minus m1g will equal m1a1y. But again, we're at rest, so we're going to assume that equals 0. We therefore can solve for n1s is equaling to n12 plus m1g. Okay. So now you know all the forces of your systems in terms of known quantities. This free body diagram wasn't really that hard, right? It shouldn't be that complicated. The ones in your homework will certainly be much, much harder. But let's try to solve something a little bit more complicated now. So now let's go back and let's think about our system, and let's imagine that we had other things acting on it. Okay. So what does that mean? Well, let's imagine we had a person, and that person was pushing on our object. So now we have a person who is pushing on these blocks to make them move. Okay. And we'll just say that for the purposes of our problem here, that the two blocks are moving together, although you'll certainly have time to sort of study those assumptions later on. Okay. So now what we'll say is, okay, this person's pushing on block number 1, and actually I'm going to change this a little bit, sorry. Believe it or not, I actually have a plan for this video. It's just not going as smoothly as I would like, given the fact that this is my first audio recording. Okay, so now the person is pushing on object 2, and the whole system is going to begin accelerating to the right. So we're going to say that the blocks accelerate together. So the blocks accelerating together is what we call an acceleration constraint. That means that A1 is going to equal A2. That's what it means when we say they accelerate as a system, they accelerate together. So the first thing I want to tell you is that whenever you're given a problem like this, and where you're told you have a system moving and behaving in a certain way, ignore the individual pieces. What does that mean? Well, let's imagine you were trying to find the acceleration of a book that you are moving in your hand. You wouldn't draw a free body diagram for each page of that book. You would draw instead a free body diagram for the entire book, and then if later I asked you what was the force between 2 pages, you would then tell me. Same idea here. Instead of assuming that these 2 blocks are separate because we're finding the system, we're going to solve it as if it were one object. So how do we do that? Well, we draw a dot, and that dot represents our system. We'll call it a little s. And then we add forces. Well, the first forces you're always going to add to a system is the weight. So we're now going to have m1 plus m2 on g. Then what you do is you trace your object like before. There's something touching this side. What is it? The person pushing. We'll assume that that person is pushing this way. So we'll say F on the system by the person. That's our convention we're using. We continue tracing around, no touching, no touching, no touching. Up, down to the bottom, you've got contact. So here you've got a normal and a friction again. So we have a normal, will be directed upwards. We know again because it makes contact with the ground, and it's the only thing supporting the horizontal forces, that normal here, the normal on the system, by say the ground, will equal the weight. So we sort of draw it that way. But if you didn't, that's okay. Later you'd solve for it, you'd find out. So now in this case, we've got a system that is accelerating to the right-hand side. So we do have a frictional force. So that frictional force we know will be directed to the left-hand side. We'll say it's friction because it's moving, it's kinetic friction. It's on the system by what? By the ground, by the surface, by whatever it is that we drew prior. So we said G over here, we'll use a G here. So one of the helpful things about this notation is that when you look at these subscripts here, these match if they come from the same surface. And that helps you because when you have kinetic friction, F sub k Sg will equal mu k, which is the coefficient of kinetic friction, times NSG. So it's important that these subscripts match. If they don't, you've done a problem. This notation is bookkeeping. It's trying to help you out. So now once we've drawn our free body diagram, we want to add a coordinate system. So we have x and we have y. And now we will begin to sum our forces. I always like to sum in my vertical direction first. I just find it makes the flow of algebra work out a little bit better. So I'm going to go through here and now sum my forces. So the sum of the forces on the system in the y direction is going to be NSG minus M1 plus M2G equals M1 plus M2 a system y. Right? But again, we've chosen our coordinate system so that the acceleration is in one direction, and it is not up and down. So our vertical acceleration is going to be 0. So that's going to be 0. Therefore, we find that NSG equals M1 plus m2 times g. Okay. So now we'll sum our forces in the x direction. We get FSP minus FK SG is going to equal now m1 plus m2 times a system in the x direction. Okay, so we have a few things we know. One, we know what this is because kinetic friction we have a formula for. So we'll go ahead and plug that in. FSP minus mu k times NSG. But fortunately, because we solved the y first, we know what that is. And so this is a point at which a lot of students often get confused. Newton's second law says that you can set the sum of these forces, right? This sum equal to MA, right? So important, the sum is this right here. The sum is not that. The sum can equal that. That's what Newton's second law is telling us. It's an important property to keep in mind. So now we look at this and we say, okay, what do we know? What do we not know? Well, presumably, if we're given the problem, we know what all of our masses are. Great. We could find our acceleration if we knew our force, or if we were given a force, we could find acceleration. In this case, I'm going to assume that we were told that force and therefore find the acceleration. So then your acceleration will be FSP over m1 plus m2 and minus mu k times g. So now we always want to check our units and make sure it makes sense. The force divided by mass is the units of acceleration. That's good. Coefficients of friction are always dimensionless. And so therefore the units that we have to worry about are g. So that is the beginning of solving free body diagrams. Now, let's say I said to you, okay, great, that's the acceleration of the system. However, what is the magnitude of the frictional force on object 1 due to object 2? So let's say that again. What is the magnitude of the frictional force on object 1 due to object 2? So let's write that out. What is F on object 1 due to object 2? And we know they're going to move together, so it's a static friction. So that's what we're being asked to find. So now in this case, we have to be a little bit more careful about it, and we have to actually do free body diagrams for our separate components. So we go back, we redraw our free body diagrams, we say which one's simpler. In this case, it's a little tough to say which one's simpler. So because object 2 has an object below it and a person touching it, object 1 has the ground and object 2. Let me try to do it this way. Object 2 has contact here and here. Object 1 has contact here and here. So they each have the same number of contacts, so therefore work your way from top to the bottom. So we'll start here. So object 2 has its weight on it, which we'll draw as m2g. We now look for contacts. We're tracing, not starting at the bottom. There's the person pushing on it. Okay. That's what was FSP before, and I'll write it as F2P now. But we know in our minds that FSP and F2P are the same thing. Okay. So we continue to trace our object. No touching, no touching, no touching. Now we have contact to the bottom. That contact results in a normal force upward, so an N on object 2 because of object 1. And then we have a friction. Now here's where it starts to get tricky. People don't always know. Is the friction going to be to the right? Is it going to be to the left? How do you know? Well, you have to ask yourself this. Let's imagine this object were going to move. If it were going to move, which way would it move? Well, if block 2 is being pushed, it's going to move to the right. So friction is going to oppose that motion, and therefore that is the sliding motion here, and therefore put a force to the left. Okay. So now we have a friction. It's static because they're moving together on object 2 because of object 1. All right. And now we see that this will be the right coordinate system to choose x and y. All right. So now with that, technically we're done. And you'll see why in a minute, but we're going to move on and just act like we don't know what the answer is, and we're going to keep solving. So now we do a free body diagram for object 1. We get its weight vector going down. So we have m1g. And now we trace looking for contacts. Again, not starting at the bottom. There is no touching, right? This person is not exerting any force here because he is not touching that. Okay, so now we have a contact here at the top surface, and so from that contact we're going to get a normal force going downwards. Sometimes people like to draw their vectors kind of weird and curved like this. Don't do that, just draw it parallel. So now we have a normal on 1 due to 2, and we know because of Newton's third law that that force is going to be equal to that force. So we look here, we also have a frictional force, and this is where, by doing the free body diagrams carefully and systematically and in order, your life just got easier. Why did your life get easier? Well, Newton's third law says that that force's third law pair has to point in the opposite direction. So we know that that force is going to be this way, and that's F12 static. And we don't have to think anything about it. It just is because of Newton's third law. I'm going to put little 2 tick marks to show that those forces are equal. All right, so now we continue our trace. No forces, up at the bottom, normal and friction again. So we have a normal force, it's going to be upward. I'm not drawing as carefully to scale right now. And that's the normal on 1 by the surface. And then there's going to be what? Some static or some kinetic friction pointing backwards. And that's kinetic friction on 1 by the surface. Again, you want those terms to match here. Okay, great. We'll give that a coordinate system of x and y. All right. So now what we're going to do is we're going to sum our forces for object 2 in the y direction. And we're going to find pretty much what we found earlier, but we're just doing it for the sake of completeness. n21 minus m2g, that's going to equal 0. Therefore, as we already knew, n21 equals m2g. Now, sum of the forces on 2 in the x direction is F2p minus F21s equals, now a lot of times people just write 0 again, but no, it isn't. It's equal to m2 times a2. Now, we already know what it is, though, because we've said the acceleration of the objects is for them accelerating together, which means those accelerations are going to be equal. So then, therefore, we can now solve for F21s, which is going to equal what? F2p minus m2a2, which is going to equal F2p minus m2 times FSP over m1 plus m2 minus mu kg. All right, so I'll try to write that a little bit more clearly. F21s is F2p minus, I'm going to write it as a ratio. We're going to learn that ratios are super important to us. Try to zoom in and make that bigger. I'm running to the edge of my screen here. I haven't figured out how to restart a video or really to edit a video, or I would start and stop and fix it. I'll try to get better at these. So what this is saying now is the friction on object 2 because of object 1, which we know from Newton's third law is the opposite force of F12s. So that's what we were looking for in the first place. We've now found it. Is equal to the force of the push minus this thing, which is kind of weird, but it's a ratio of the forces. And we'll look into things like that a lot. You should ask yourself right now, like, what happens if if M2 is really large? What happens if M1 is really large? And then you have this force here, which is what? That's related to the coefficient of static friction from the ground beneath you. And that doesn't look right to me with that M2 in it, so I'm going to go back and see if I didn't bumble something up. Nope, I've got that right. Okay. So there's your answer. Hopefully you're able to do that yourself on problems at 0. It might take several attempts to get to it over time. I'm going to stop the recording now and try to upload it. Thank you.